Good morning. How are you? How was your homework? How was your homework? Quite involved, huh? We had to use the definition of the derivative to come up with formulas for the derivative function or evaluate the derivative at a given number. And sometimes the problems were pretty involved. We had to apply limit laws in each case to find out what the derivative was. Well, there's good news. The good news is that not always we will have to do that. We will develop formulas, we will write down formulas that in some cases will enable us to quickly get the derivative based on the derivative of a function that we already know. For example, today we will write down formulas how to differentiate polynomials and the exponential function e to the x. We will also start to write down more and more rules that eventually will enable us to take derivatives of quite complex functions without going to the definition. In some cases, we will have to use the definition. That is usually when a function is defined using several formulas, and when we stitch different formulas, these are the numbers at which we cannot apply rules, because in a neighborhood to the left of that number, the function has a different formula, and to the right of that neighborhood has a different formula. So these differentiation rules will not be applicable. Okay, let's start. So what is the most basic function? X. Y of x is equal to x. Well, that's a pretty basic one. It's the identity function. But how about a constant? Let's start from considering the function f of x, which is a constant function. Let that constant be c. So if we have a function whose only value is one number, it's number c. So at any point on the graph of that function, the slope is obviously what? It's 0. So then we expect that if we have a constant function, so c is a constant here, then the derivative of a constant is 0. Let me illustrate how we prove these things formally using the definition of the derivative. So today we will work hard, or perhaps not so hard, but we will prove our statements using the definition of the derivative, so that in your homework you will be able to quote these theorems, and no longer will you have to find the derivatives using the definition. So how would we prove this? Well, by definition of the derivative, so that was the limit as h goes to 0 of f of x plus h minus f of x divided by h. But in our case, the derivative, the function f is a constant. So what we get here is f of x plus h, f of anything will be c. So we have 0 over h, which is 0, and the limit of 0 is 0. So that concludes our proof. The derivative of any constant is always 0. Okay, so now let's go back to the function that one of you suggested as being one of the most simple one. That's the identity function. So its graph is the line passing through the origin, and What's the slope of this line? At what number? So the slope is 1 at, say, the number -2. The slope of the tangent line is 1 at -2, and at 7 will be also 1. So everywhere, the slope of the tangent line to the graph of f of x is equal to x is 1. So we expect then that the derivative f prime of x will be equal to 1. And in fact, that's the case, supported by our geometric interpretation of the derivative. So let me prove this again. So I will prove that the derivative of x is 1. Here the differentiation is with respect to x. Again, we will use the definition. So the derivative of x by definition of the derivative function is the limit as h goes to 0 of f of x plus h minus f of x divided by h. So that is the limit as h goes to 0 of, what's x plus h? F of that? Well, f is the identity function, so it will be x plus h. And f of x is just x. So what we get is the limit as h goes to 0 of, what's left in the numerator? X plus h minus x. So it's just h, right? Okay, so we get h divided by h, which is 1. So we have the limit of 1. And you know that the limit of 1 of any constant is that constant. So we just proved that the derivative of the identity function is 1. And in the beginning, we proved that the derivative of any constant is 0. Okay, so what's the next step? We already have the constant, the identity function. So now we probably would like to come up with a formula for the derivative of x squared, x to the third, x to the fourth, in general, x to the n. So now I'd like to do that. Let us guess what the formula for the derivative of, say, x cubed might be. I'm sketching a graph of the function x cubed, and I would like you to graph slopes of that function. In other words, to graph the derivative of this function x cubed. Okay, we don't need an exact graph, but just something that would allow us to guess, enable us to guess the formula. Well, at 0, the graph of x squared has a tangent which is 0, right? The slope of the tangent is 0, so probably, well, not probably, but the graph of the derivative will pass through 0, 0 as well. If x is negative, what are these slopes? Are they positive or negative? Quite positive. So if x is very negative, the derivative of x cubed will be quite positive. So probably the derivative here will start with positive values, somewhere like this. And then as I move towards 0, the slopes of the tangent lines becoming more and more flat, so their slopes are decreasing actually to 0. So somehow this function has to decrease to 0. And then to the right of 0, look, the slope is 0, but then it becomes more and more positive. So as I go toward infinity, the slopes are becoming positive, more and more positive. So I guess my question is, what did I sketch? What kind of function did I sketch? A parabola, right? Okay, so this is probably something like x squared. But the question is, well, is it really x squared, or is it x squared times a constant? And I'm about to prove that actually the derivative is 3 times x squared. So let's do that. And what I will do is, let me remind you the definition of the derivative at x to be the limit of the ratio. And right now I will let x plus h to be b. I don't have to do that. I mean, you can use the original, the definition, the equation that we used in just a couple of minutes before. But I'll just illustrate an alternative proof without using the h. The proof that the derivative of x to the n is n times x to the n minus 1. So this we're about to prove right now. So if I let x plus h to be b, then in the definition of the derivative, b will go to x. And then I have the difference of f of b minus f of x divided by b minus x. Okay, so let's prove this. So the derivative by the definition of the derivative of x to the n by the definition of the derivative is equal to b goes to x of f of b minus f of x divided by b minus x. So this is equal to the limit as b goes to x of b to the n, right? Because the function f of x is x to the n, so f of b is b to the n minus x to the n divided by b minus x. And now, as in the previous lecture, I need to find a way to factor out the numerator so that I can divide the numerator and the denominator by something that goes to 0. Because as it is, I have two quantities, the numerator and denominator both go to 0. So as it is, I'm not able to solve this limit problem. Let me remind you a formula which allows us to factor the numerator. So b to the n minus x to the n is equal to b minus x times b to the n minus 1 plus b to the n minus 2 times x plus the other terms. And these terms have the following pattern. You decrease the power of b by 1 and you increase the power of x by 1. So the last term is x to the power n minus 1. And if you don't remember this formula, you can get convinced that this formula is correct by simply multiplying the right-hand side, and you will see that all the terms get simplified except for these two. Okay, so now I'm rewriting the numerator. And I get the limit as b approaches x of b minus x times b to the n minus 1 plus b to the n minus 2 times x, these other terms, and the last term is x to the n minus 1 divided by b minus x. So since in the limit, as b approaches x, b is never x, I can divide the numerator and denominator by b minus x. And then I get the limit as b approaches x of b to the n minus 1 plus b to the n minus 2 times x plus x to the n minus 1. Okay, now we have a summation. Each term has a limit. It's actually a polynomial in B, so I could just use a direct replacement rule or just follow the limit laws. The limit of the first term as b approaches x is just x to the power n minus 1. The limit of the second term will be x to the power n minus 2 times x, and so forth. In other words, I'm allowed to replace b with x everywhere. So, but I'll do it step by step, just to make sure that you understand how I'm applying the limit laws. So, at the moment, I am splitting the limit of the summation into the sum of limits. And the last limit is the limit as b approaches x of x to the n minus 1. So the first limit as b approaches x of b to the n minus 1 is x to the n minus 1. The second, b to the n minus 2, x here is not, it does not change, so the limit here is x to the n minus 2 times x, which is x to the power n minus 1, plus, notice that in each term I have b to some power and x to some power. But the sum of the exponents is always constant, and it's always equal to n minus 1. So each term in the limit will be x to the n minus 1, actually including the last one. So how many of these terms do I have? 1, 2, 3, 4, how many? Well, let's take a look. Here it's the first, the second, so the last one is the nth term. We have n terms. So it's n times x to the power n minus 1. And that's exactly what I wanted to show. There's an alternative proof using the definition that involves just the variable h that goes to 0. In this case, one applies the binomial theorem, and I included this proof in the notes. But before you look at the notes, I encourage you to try to do it on your own. So the derivative of x to the n is n times x to the power n minus 1. That's why the derivative of x to the third power is 3x squared. Okay, so we derived that the derivative of x to the n is n times x to the n minus 1. And now, what about if we have functions which are, say, summations? Say, x to the third plus x to the 7th. In order to differentiate a sum, it'd be nice to say, well, that's the derivative of x to the third plus the derivative of x to the 7th. So in other words, we would hope that we have a rule which enables us to differentiate term by term if we have a summation or difference. And that's actually the case. Let me state these rules. If you have two differentiable functions, at x, then the sum is also differentiable at x. Maybe let me write down clearly that these functions depend on x. So this function is differentiable at x, and its derivative is equal to the derivative of f plus the derivative of g. Similarly, we have a rule that if you have the difference of f and g, then you can differentiate the difference term by term as well. And if c is any constant, then if we differentiate that constant times the function f of x, and we can just pull that constant outside. This is a constant times a function. This is not the same thing as saying that the derivative of a constant is 0. Okay, so what I'll do is I will prove just one of these statements so that you can get a glimpse of how this proof proceeds. It uses the definition of the derivative and properties of the limits. And the other proofs are quite similar. So perhaps why don't I just do this, the summation rule for differentiation. Okay, so to prove one, how about if I start from the right-hand side? It'd probably be a little bit easier. Remember, one way to write the definition of the derivative was the definition of the derivative of f at x was the limit as x goes to b of the difference f of b minus f of x divided by b minus x. So I'll use that formulation here. So I'll start with the right-hand side. I'll write down the definition of the derivative of f of x, the definition of the derivative of g of x. Then I'll apply properties of limits, and hopefully I'll get an expression that will be the definition, the derivative of the summation. So let me do this. So the summation of the derivatives. So by definition of the derivative, f prime of x is the limit as b approaches x of f of b minus f of x divided by b minus x. And g prime is the limit as b approaches x of g of b minus g of x divided by b minus x. So I have a summation of two limits. And remember, one of the limit laws allowed us to combine these two limits into one. So I have the limit as b goes to x of b minus x in the denominator, f of b minus f of x in the numerator, plus g of b minus g of x, all of that divided by b minus b minus x, I apologize. Okay, so what's the next step? I have a common denominator. So I can combine these two fractions into one. So I got the limit as b approaches x of, the denominator is b minus x. What about the numerator? I'll have f of b minus f of x plus g of b minus g of x. Okay, so I should write this down, but I'd like to skip one step here and reorder the numerator. I'll write f of b first, then g of b, and then f of x, and g of x. What will we do now? What is it that we're getting? We're trying to get the derivative of the sum of f and g. So in order for us to get the sum of the derivative of the sum, I need to get the limit as b approaches x of, and what do I write here? The function, which is the sum of f and g, evaluated at b. So how about if I call that function k of x? So I need to get something like k of x k of b minus k of x divided by b minus x. So that will be k prime of x, which is f of x plus g of x prime. Okay, so we're missing this transition. So what was k of b? What is it? K of b is the summation, so it will be f of b plus g of b. That is k of b. And what's k of x? F of x plus g of x. So that's k of x. But notice that these two things are the same. So by going from like one side and the other side, eventually we were able to write down a sequence of limit transitions. And what did we show? That the sum of the derivatives of two functions f and g is equal to the derivative of the sum. So that's why we can now differentiate x to the third plus x to the seventh by simply differentiating term by term. So f prime of x in our example here will be simply x to the third prime plus x to the seventh prime. So that's 3x squared plus 7x to the sixth. And I apply the power rule. Okay, so let's conclude the lecture with the derivative of the exponential function. We're now ready to talk about the derivative of the most important function in mathematics, which is the exponential function, e to the x. Let me define the function e to the x, or rather sort of illustrate what e, the number e might be. Okay, so how do we prove this? Well, again, we will use the definition. So the derivative of e to the x by definition of the derivative is equal to the limit as h goes to 0 of e to the power x plus h minus e to the power x divided by h. E to the power x plus h is f of x plus h. E to the x is f of x, right? So I'm just applying the definition of the derivative here. This is equal to the limit as h goes to 0 of, and unlike in the previous examples, we're able to factor some term in the numerator and divide it by that term in the denominator. Here, I don't think we're able to do that. We're not able to factor out h from the numerator. But what we can do is, remember what one of the properties of the exponential function is that if you exponentiate the sum, it's the product of the exponentials. So e to the x plus h is e to the x times e to the h. Okay, so this is the limit as h goes to 0 of, and what can I do here? I see e to the x, so I can factor e to the x. So I have e to the x times e to the h minus 1 divided by h. Okay, but notice that e to the x does not change as h varies. So for the purpose of that limit, it is considered as a constant. Since this does not depend on h, I can take it outside of the limit. And then I get the limit as h goes to 0 of e to the x times the limit as h goes to 0 of e to the h minus 1 divided by h. Okay, but what is this limit? I'm not asking a dumb question. Emily. Just wrote this down. That limit is 1. So we get e to the x times 1, which is e to the x. So if you grant me that I defined e to be this number that satisfies this limit, e to the h minus 1 over h is 1 in the limit, and the geometric interpretation of this limit is that that's this number at which, if you look at the family of exponential functions, a to the x, and if you look at the slope of the tangent at 0, 1, and if that slope is 1, so that particular number, 2.71, that satisfies that condition is e. So based on that, we were able to derive the formula for the derivative of e to the x. Well, let's conclude the lecture with maybe one. Let's differentiate x to the third plus the square root of x plus 3 times e to the x. Well, first, what you see is the summation. So we can differentiate every term separately and add them up because we had the sum rule for the derivatives. So we get the derivative of x to the third plus the derivative of the square root of x plus the derivative of 3e to the x. The derivative of x to the third, we will apply the power rule, which was, what did the power rule say? That the derivative of x to the n is n times x to the n minus 1, right? N here is 3. So the derivative of x to the third is 3x to the 3 minus 1. Now I need to differentiate the square root of x. And remember that I mentioned that the power rule even holds for fractional powers. So I can rewrite this as x to the power 1/2. Then the power rule will give me 1/2 x to the power 1/2 minus 1. And finally, 3e to the x. Here I have a product of a constant and function, e to the x. Remember, the constant rule allowed us to take the constant outside of differentiation. So we get 3 times e to the x prime. And so we get 3 times x squared plus 1/2 x to the power negative half plus 3, and the derivative of e to the x is e to the x. Look how quickly we arrived at the final answer. We no longer have to follow the procedure to do all the limits, the definition, and so forth. The homework in this section, in this lesson, is not difficult, but it's a little bit tricky. Please pay attention to the rules. And while you do not have to use the limit definition of the derivative, I'm asking you to spell out which rule you are using in order to get the answer. Do you have any questions? No questions? Well, let's look at the homework. Maybe I can get you started on the problem. Well, let's differentiate, say, x plus 5 times 2x minus 1. How would you do this? You would multiply it first and then take the derivative. And what would you do? You take the derivative of the first term and multiply it by the derivative of the second term. And what would you do? Okay, I would also first multiply the terms and then take the derivative. You know why you cannot do that? Because we don't have a rule which allows us to take the derivative of one term and multiply it by the derivative of the other term. There is no product rule like that. Since we don't have a product rule, let's just expand the expression in the brackets. We'll get a polynomial. And then since a polynomial can be differentiated term by term. So x plus 5 times 2x minus 1. So we get 2x squared minus x plus 10x minus 5. And then I need to differentiate this. Let me simplify this expression. So it's 2x squared plus 9x minus 5. By the way, in general, it's always a good idea to prepare your expression to be as simple algebraically as possible before you differentiate. That suggestion holds true now and lessons to come. Before you differentiate, try to simplify the expression as much as possible. That will save you a lot of time. Okay, so now we differentiate term by term. The derivative of 2x squared, 2 is a constant, so we factor it outside. The derivative of x squared is 2x. 9 is a constant, we factor it outside of the differentiation. The derivative of x is just 1. And the derivative of 5 is a constant, so the derivative of 5 is 0. So our final answer is 4x plus 9. Well, thank you for your attention, and I will see you next time when we will have a product rule, as you but not the kind of product rule you suggested. Because I think what you suggested was to say that f of x times g of x, and if you take the derivative of that, that's just f prime of x times g prime of x. So that is not the case. And if you cannot wait until we meet next time to find out what the product rule is, why don't you read on or try to guess it perhaps? It took mathematicians a long time to guess it right, but you know, it was a long time ago. Okay, I'll see you next time.